Hello again, nice to be back. I'll be talking about the seL4 core platform. What is the seL4 core platform and why do we need it? Well, anyone who has tried to build things onto seL4 probably has an appreciation of this. Someone said this 5 years ago, with seL4 we achieved unprecedented levels of security and user unfriendliness. And that's really what it is. It's not particularly user-friendly. Actually, that wasn't me. Okay. So, what is the issue with using seL4? Well, the one is that the API is really, really low level. And this is part of the reason is partially because of its generality. We wanted to build this verified kernel. And because the effort of verification is so big, we wanted to make it worthwhile by making the system as applicable, as general purpose as possible. Also, keeping it small and low level really helped verification. It simplified the code base. But also the fact that memory management is exported to user level both helped verification of the kernel itself. It helped our security proofs, so this is a really important characteristic of seL4. And from the operating system design point of view, it's probably the most revolutionary bit of seL4. And because it's so low level, it's architecture dependent. So the API does not provide a complete hardware abstraction, and that's intentional, because as soon as you abstract, you introduce policy, and we want to keep seL4 as policy free as possible. And needless to say, it's extremely Spartan. There's not a lot of environment around it, and you have to BYO a lot of what you expect from a normal operating system. And therefore, for those and other reasons, a lot of expertise is required to build things on seL4 and build them correctly, have a good design. We want to take the pain out of this as much as possible. The seL4 platform is designed to support what we see at the moment as the dominant use cases. Almost all deployments of seL4 are in the embedded and cyberphysical space, and they're basically static, simple architectures. And because that's at the moment the predominant use case, this is what the core platform is support. Notice the difference in emphasis here and intention. seL4 itself is meant to be really broadly usable, general, and policy free for that reason. And with the core platform, we narrow on a fairly specific application area which implicitly introduce a lot of policy. So the policy freedom in many ways is gone. We try to retain it in some other aspects, and you'll see that when you get to see the core platform at a bit more detail. So specifically, the aims are to provide support for this use case of embedded cyber-physical IoT systems, etc. Ease of development is obviously the main driver. That was the motivation I gave. You want to achieve what operating systems give you in general: application portability with defined hardware interfaces, support for implementation diversity. For example, you want to be able to use different network stacks or different file systems depending on your actual use case. And you want to be able to reuse components that use this platform between related deployments. So these are fairly general operating system aims. In seL4 specifically, where it's so tricky and requiring a lot of insight to use the mechanisms correctly, we want to make this easier by basically, for the particular use case, bake in the right use of the seL4 mechanism. So you don't have to be an expert in the seL4 API to build a good system anymore. Beyond that, we want to retain a lot of the strength of seL4. So the minimal trusted computing base, which means the core platform itself is going to be very small. We want to use the seL4 enforced isolation for security and safety as much as possible, and retain that for the user level software. And of course, really close to my heart is we want to retain the trademark performance of seL4. It's no point building an operating system on the most efficient, most performant microkernel in the world and build on top something that is slower than other systems you're used to. That would be a major loss, and the core platform specifically tries to avoid that. And given that we have built this verified microkernel, we want to be able to pull the verification higher. So the abstractions of the platform are meant to be simple enough to enable verification of higher software levels. Ideally the whole TCP, which of course includes the whole core platform and a few other more application-specific parts. Okay, how do we do it? What kind of design do we use? Of course, it's POSIX compliant, right? Wrong. It's not POSIX compliant. It's very much not POSIX compliant for very good reasons. Why? Well, Curtis is giving a talk, or has just given a talk, so you should know all about it. In a nutshell, POSIX is well past its use-by date. It's definitely too inefficient for the kind of systems seL4 is being deployed in, and we really want to depart from it. Okay, so what do you do with your software stacks that are built for POSIX system and you want to reuse on seL4? Well, for that purpose, we provide virtual machines. So put your legacy stacks in a virtual machine where they don't pollute the rest of the high assurance system. That's the approach. So what does the core platform look like? Well, and a lot of these are in very explicit opposition to POSIX. A simple execution model, that's definitely non-POSIX. Simple communication model, that's definitely non-POSIX. Real-time capable, that's important for a lot of our application cases. Efficient, that's definitely not POSIX. Deadlock-free, enforceable by build tools. That's important for a lot of systems you build, and you don't get that in POSIX. And we want to be able to enforce as many as other integrity properties that are important for these kind of systems by build tools. And the APIs, the abstractions we offer for that are geared towards that. And as I said earlier, suitable for formal reasoning. So you want to be able to reason about the abstractions and the software built on top of them, but also the software that implements the core platform. And because of the usage domain we are envisaging, we have a certain hardware model behind this. So we're looking at homogeneous multi-cores. That doesn't mean you can't have accelerators on that. So there is a degree of heterogeneity is allowed, but these accelerators, they're basically devices. So if you have a GPU or some other accelerators, that's fine. But they're devices that don't run the operating system kernel. As far as the general purpose cores that run the operating system's kernel, the operating system, the assumption is that they are homogeneous. We can argue whether sort of the ARM big little endian architecture, that is homogeneous enough. It's homogeneous in the ISA, so that would still fit. It's a single system image, and that means we definitely restrict ourselves to a relatively small number of cores. It's a uniform memory access, so again, that's representative of the typical embedded processors, and I already mentioned accelerators. Okay, so that's the sort of core hardware we're aiming for. And then the abstractions are, as I said, fairly simple. There's a very small number of them, very small. We have communication channels, we have protection domains, we have memory regions, we have notifications, and we have protected procedure calls, and that's about it. There's a half abstraction more than. So in terms of the conceptual complexity, this is definitely very simple, but it serves most, if not all, of the systems we have experienced in the past 10 years in terms of real-world deployments. Okay, let's go through them. The first one is the protection domain. What's a protection domain in the core platform? It's very superficially similar to a Unix process, but it's definitely way more lightweight. And because it's obviously built on seL4, so it consists of seL4 objects, and specifically it has a space, a virtual address space. That means page tables. It has a C space, that's a capability space, so that represents the access rights the protection domain has. It has a scheduling context. So those familiar with seL4, that means it's definitely aimed to work on the MCS kernel, not the traditional L4 kernel. And this is totally in line with what I said on Monday, that any new development should be built on the MCS kernel. We will not support or encourage new system development on the old kernel. Use MCS, and the core platform definitely is built on the MCS kernel. We have a protection domain also has a priority, and it has a notification. So the notifications in this core platform are always associated with protection domains. What the protection domain contains, its code, is structured in 3 functions. There's an init procedure, which gets called once at system initialization time, and it executes on the priority and with the scheduling context of the protection domain. Makes sense, right? That's what they have a priority and a scheduling context for. And then there is a notification procedure, and this one is invoked when the PD's notification is signaled. Remember, I said a protection domain has a notification, and whenever that is signaled, then the notification procedure is invoked. So this makes an event-driven programming model for protection domains, and that's pretty much where it is. There's this, in the machinery behind, there's an event loop, and what it does is it invokes a notification procedure when the notification comes in. And then these 2 are mandatory, and then optionally it has a protected procedure, which can be invoked from another protection domain. And unlike the notification procedure, which runs on the protections domain's own priority and scheduling context, this runs on the invoker's scheduling context, but still the invokee's priority. So again, this is a property of the MCS kernel for good reasons. Importantly, this is all sequential. There is no concurrency control needed. The core platform guarantees that these functions will never run concurrently, so they are atomic with respect to each other. And they may interact with other protection domains by signaling or by making a protected procedure call. And that's it. That's basically the programming model. Right, that was the protection domain abstraction. The next abstraction is the memory region. And a memory region represents physical memory. It is contiguous, it's power of 2 aligned and aligned to its size. Sorry, power of 2 in size and aligned to its size. And what you can do with a memory region is map it into a protection domain at a particular virtual address. You can specify caching attributes and permissions. And the memory region may be mapped multiple times within the same protection domain or within different protection domains. Of course, that supports shared memory communication. A protection domain may also attach to a communication channel, in which case it provides a shared buffer for the communication, for zero copy communication. And that's it as far as memory regions are concerned. Okay, next abstraction are communication channels, and they support pairwise communication between protection domains. So every channel has exactly 2 protection domains it's associated with, and that obviously means if you have n protection domains in your system, there are at most n squared communication channels, or n squared half. Data flow through a communication channel can be unidirectional or bidirectional. That depends on how the specific communication channel is configured. But from the security point of view, information is always bidirectional. So you cannot have data diodes on this simple model. Okay, what kind of operations can you do on a channel? You can read or write to the memory region of the channel, assuming that it is mapped into both of the protection domains that are connected by this channel. You can reference locations in this shared memory buffer, not by pointers, but by a specific reference wrapper mechanism. And you can signal another protection domain's notification. So this is how signaling works. You don't have explicit references to signals. Signaling is part of the communication channel. And if a protection domain offers a protected procedure, then another PD connected to it via such a channel can invoke that protected procedure. And of course, that invocation can only happen if the target domain actually exports a protected procedure. Or I said that already. You are not allowed to reference to pass pointers to this shared memory region. You need to have a wrapper mechanism so that that data structures work correctly. It's important to notice that there is no implied trust relationship between protection domains that share a communication channel, and there is no restriction on cycles in the channel. So you can have a protection domain 1 have a channel to protection domain 2, 2 has a protection domain channel to protection domain 3, 3 has a channel to protection domain 1. So channels are allowed, and so they form a non-directed cyclic graph. Okay, that was it about channels. And the next one is notifications, which are already mentioned. They are associated with protection domains, and they get signaled through this communication channel. So if you have two protection domains sharing a communication channel, then one protection domain can signal the other one. And of course, that is used for synchronizing communication when you use zero-copy communication via the message register, the memory region associated with the channel. So in particular, notifications support triggering of events. So you can signal another PD's notification if you're connected to it via a channel, in which case that will trigger the platform to invoke the notification procedure of the target protection domain. Remember, when I initially talked about protection domains, I said each one has a notification procedure. Well, this is exactly how you get it activated by signaling the protection domain. The platform uses batched capabilities to identify the sender of a notification, and that means, okay, if a protection domain has different channels connecting it to a number of other protection domains, then these channels are invoked, or the notifications through these channels, the signaling through these channels uses capabilities with different batches, so the receiver can distinguish between them. Signaling is of course asynchronous because that's the underlying seL4 mechanism it uses. Because notifications, seL4, low-level notifications are binary semaphores, the same applies to the notification model in the core platform, and that means if you quickly signal a notification multiple times before the target protection domain gets around to processing them, then they get lost. But this is how binary semaphores work. And the loss of data is can be avoided by setting the priorities right. But depending on your use case, this may or may not be an issue. You may or may not have to think about it. The processing of multiple notifications, so if a protection domain A is connected to multiple channels and therefore multiple partner protection domains, then, and if those concurrently signal the notification of the first protection domain, then, okay, what is the order in which these signals get processed? Each of these will cause one invocation of the notification procedure, once for every sender of the notification. The order in which these get processed should be the priority order of the protection domain sending them. And of course, if they are at same priority, then that doesn't necessarily imply a strict order, although underlying there will be a fixed order implied depending on how the batch bits are associated or allocated. And this, in priority order processing, should be enforced by the platform tooling. I said should be because in the first release it may not be, but that's definitely intention that this would be automatically enforced. And of course, because this is built on seL4 notifications, and seL4 notifications on a 64-bit platform have 64 batch bits. That means a protection domain can at present only have up to 64 channels. This is plenty for the kind of application the core platform is aimed to support. So I don't foresee an issue there. Eventually this will grow and we'll have to use a more sophisticated mechanisms, but I don't see that become a bottleneck anytime soon. Right, these are the notifications, and then we have protected procedure calls. What are they? They are what people call IPC, but this is really a terminology we should not really use. You should always see IPC as a way of implementing protected procedure call. And a protected procedure call means you execute some code in a different protection domain. And this is exactly what our protected procedure calls provide. So obviously you can only do a protected procedure call if the callee actually has a protected procedure. Remember, that is optional. If a protection domain does not provide a protected procedure, then obviously you can't do a protected procedure call on it. The other prerequisite is obviously, in order to invoke the protected procedure, you need to share a communication channel. Goes without saying, because there's no communication without communication channel. And in a protected procedure call can pass arguments. They may reference locations in the channel's memory object, but not by naked pointers. You need to protect them by wrappers to make sure that the addresses are correct. And again, this is something that the platform should be able to enforce, eventually at least. You can have nested protected procedure calls. So PD1 may call PD2, which in turn calls PD3. That's totally valid. And this is sort of, it has all the flavors of a client-server model. In this case, protected procedure calls, unlike communication channels in general, are an asymmetric relationship. Asymmetric in at least two different ways, namely that the caller trusts the callee. So in that sense, the callee is sort of at a higher trust level than the average caller. So servers need to be trusted to a degree. But also the callee must run at a higher priority than the caller. And you quickly notice, of course, that this already guarantees that there's no deadlock in the system. You can have nested protected procedure calls, but because of this priority rule, there cannot be any cycles and therefore no deadlocks. Again, this is something we want to enforce by build tools. Eventually, probably not in the first version. Also, for sanity of the whole system, given that this is all event triggered and the functions execute relatively atomically, a core condition is that a protected procedure must not block. Again, this should be enforced by build tools, may not be in the initial version. Okay. that are the main abstractions. There is still a half abstraction to come, and that's virtual machines. I call this a half abstraction because a virtual machine in the core platform model is nothing but a protection domain with some extra attributes. So in every respect, in terms of the other protection domains, this behaves just like a protection domain. The specific attributes it has are used for being able to run tests in kernel mode. So they have at least an extra execution mode, which is the guest kernel mode, and a few other things that are required for virtual machine state. But beyond that, it just behaves like a normal protection domain, so it can share memory regions with other protection domains. It can signal, it can be signaled, so it communicates via a normal communication channel with the other protection domains, and it can even provide a protected procedure or call other protected procedures. And again, the priority rule applies here. And that's it. That's basically our seL4 core platform. Just a few things to keep in mind about there. Initially, we will require all protection domains to be single core, so single threaded. That avoids a lot of complications initially. The whole thing will be able to run on multi-core platforms, but as I said, initially only single threaded protection domains. It's fairly straightforward, or will be fairly straightforward, to remove these restrictions for pure client protection domains. And a pure client, when I say pure client, I mean something that cannot be used as a server, or in other words, a protection domain that does not have a protected procedure. These ones that cannot be invoked as servers, making them multi-threaded is not going to be too particularly difficult. Allowing servers to be multi-threaded is a bit more tricky, mostly working out the right model for making this happen and not introducing too many complications into the core platform. So for now, we're punting that part. For the time being, at least, we target a static architecture, which means all protection domains are known at build time. That doesn't mean that we can't support late loading. For example, the system may start up with a subset of its protection domain and others are loaded on demand. But for now, they definitely have to be all configured at system build time. Okay, and this is pretty much the overview of the seL4 platform. As I said, it's designed to make life easier for constructing well-designed seL4-based embedded systems. So the emphasis is really on well-defined. And as you can see, the abstractions are sufficiently constrained in their expressiveness to make sure that they map onto seL4 in the right way, the way you should build seL4 systems. It's not the only way, but for the target domain, we believe this is actually the best way. What's the status? We have mostly completed the design. I was hoping by today I could announce that the initial design is complete and that we have a request for comment out for community feedback. Unfortunately, we're not quite at that stage. Hopefully, it will only take us a few more weeks, but you can definitely expect an RFC with the details of the seL4 core platform for community feedback, and we're definitely hoping to get a lot of feedback from all of you. The core platform will integrate with the seL4 device driver framework, which is the next talk, Ihor just after me, which actually the last talk in the summit. And importantly, we will put actual effort in providing training material around this. So it's really important. I really realized that one of the shortcomings in the seL4 ecosystem is good training material. We talk a lot about what is good design for seL4 based systems, or more likely what is bad design, and we don't really give enough guidance. So providing the seL4 core platform is one important step here, but to be complete, it really needs to be accompanied by good training material, and we are committed to providing that. So we will make best practice training material around the seL4 platform publicly available for free reuse by anyone, and hope to use that to build up the training ecosystem for seL4 as well, including certifying seL4 instructors and training modules, etc. Okay, that's it. Happy to take any questions you might have.